everybody. Welcome to Measure Theoretic Probability. My name is Jem. I really thank you for signing up for this course because that means that it runs and that means I get to teach it and it is a lot of fun. Measure Theoretic Probability is an advanced course and presumes that you've already taken a regular course in probability where you've probably dealt with urns and balls and random variables and distributions like the binomial distribution and the exponential distribution and associated functions known as PDFs or probability density functions. And this looks nothing like that. Nothing at all. Measure theory is a language, and you probably know of a culture that's different from yours with a language that's different from yours, where they have an expression for something that just doesn't translate, or vice versa. You know, some things are easier to say in some languages over others. And measure theory is a language with which we can talk about probability, and some things are going to be easier to say. And some things are impossible to say without it. And one of the things that people usually tout when they're trying to advertise a course in measure theoretic probability, one really neat thing about it is that it unifies discrete and continuous stuff. So if you're working with a discrete distribution versus a continuous distribution, you're going to be summing things. In the continuous case, you're going to be integrating things. And whenever you prove something in that kind of course, you maybe want to prove it in both cases, but your instructor will say, I'm going to prove it in the discrete case, or I'm going to prove it in the continuous case and leave the other one to you, or the other case is similar. And with measure theory, we don't have that problem anymore. So it's really nice in that it unifies the treatment of discrete and continuous random variables and probabilities. So let's get to it. Measure theory revolves around sets. And here is a set or region that I'm going to sketch for you in R2 in the plane. So a two-dimensional space. And I want you to pause the video and measure this set for me. So I'll wait right here. I suspect that you are in one of two camps. Number one is you might be trying to find the area of this set and finding it very difficult because it's an irregular set. And how are you going to find the area? And the rest of you are probably thinking, well, what do you mean by measure this set? I could mean area, but I don't have to mean area. This is, you know, if we go back to 1D, we could talk about length, and in 2D, area, and in 3D, volume, and in n dimensions, the n-dimensional version of volume. This is one way to measure sets in these different dimensions, and this is known as the Lebesgue measure of these sets. But there are other things we can do, I guess. The problem is we need to define what measure means. So we're going to do that pretty early on in this course. One idea might be to find the length of the longest line that connects 2 points in this set and is completely contained in the set. Another idea might be to find the area of the smallest circle in which this set can be inscribed. There's many possibilities, but again, we need to define what is meant by measure before we can tell whether or not these things will count as measuring the set. So let's get started. We're going to start with a non-empty set omega. This is an abstract thing. It doesn't have to be a set of numbers. It can be very, very weird. Now, if we want to tie this back to our sort of usual regular probability course, this is going to be like the sample space of an experiment, which is the set of all possible outcomes of an experiment. So suppose that experiment is that I flip a coin, fair or otherwise, I flip it twice. I can get heads heads or heads tails or tails heads or tails tails. So there's 4 possible outcomes in the sample space. For us, this is just a non-empty set of things, and it's pretty abstract, and it's not usually connected to an experiment, but this exercise of connecting things to regular probability will be useful for grounding us as we go through the course. So we're going to start off with omega. It is a non-empty set of things, but you can think about it as a sample space in regular probability. Next up, I want to look at a set A that is a subset of omega. So to ground this in regular probability, this represents some event. And in our coin tossing example, this might be the event that we see at least one tails, which means that we can talk about this event, A, by defining a set. And A will be the set of outcomes that have at least one tail. So there's 3 outcomes there in our 4 total outcomes. Again, in this class, it's going to be pretty abstract. So omega is a non-empty set and A is some subset. And there isn't a coin. There just isn't. But again, we can ground ourselves and try to relate each thing we do in here to what it would be in a basic probability course. Now, in our coin example, and for simplicity, let's just assume the coin is fair, so equally likely to come up heads and tails. We can talk about the probability that A happens. And when you write A as A is the event, we get at least 1 tails. I think we know what that means. We get either heads, tails, or tails, heads, or tails, tails. And that's 3 out of 4 equally likely outcomes. So the probability of A happening is 3/4. But when you look at A as a set, like the set of heads, tails, heads, and tails, tails, A happening means that you perform the experiment one time and your outcome is in the set A. And the probability that our outcome is in the set A, which consists of 3 things, of 4 things that are equally likely, that probability is 3/4. But omega is just a non-empty set of things, and A is just a subset of omega. And this P for probability is just its own thing outside of an experiment. It's going to be a function that takes in subsets of omega and spits out numbers between 0 and 1. Now, if we continue with our coin example, then we know how to write down the probability of getting either tails heads or tails tails, something like that. And we can go through the power set for omega, which it means the set of all possible subsets of omega. So singleton sets consisting of 1 outcome, all double out, all pairs of outcomes, which 2 flips each. So like heads, heads, and heads, tails in a set. All triples, we can look at the whole set, and we can even look at the empty set. The empty set represents the event that nothing happened. When you flip that coin twice, something has to happen. We will not have that nothing happens, and the probability assigned to the empty set had better be 0. Again, we can go through all the sets in the coin experiment and assign these probabilities, but this is going to be really tedious for bigger sets, and especially if we have even like uncountably infinite, we have an uncountably infinite set. It's going to be awful. It's going to be impossible. So maybe we can assign this P function for probability to some subsets in omega that can then be used to extend the P function to other subsets of omega in a kind of natural way. That's going to be our goal. So first, I want to define what subsets of omega we want to look at. I'm going to let omega be a non-empty set. That is the line that precedes everything we do in here. And I'm going to let this curly capital kind of script calligraphy F be a collection of subsets of omega. Now, this doesn't have to be all subsets. It doesn't have to be power sets. And if you'll bear with me for a few moments, we'll get to some examples. But I want this collection to be called something known as a field, or equivalently in algebra. The definition of a field or algebra is a collection of sets, F, subsets of omega, such that you have 3 properties. Number 1, or I, it needs to contain omega itself. So omega is a subset of omega. When I say subset, I don't mean a proper subset necessarily. It needs to contain omega for us to call it a field or algebra. Number 2, it needs to be closed under complements. This means if you take a set A in your field or algebra, I'm going to stop saying or algebra, but if you want to say algebra, go for it. If you take a set A in your field, the complement of A needs to be in that collection as well. And the third point in the definition is that it's closed under finite unions. So if you take sets A1 through AN that are in F and you union them all together, the result is another set in omega. Is it in F? It needs to be if F is going to be a field or algebra. If you want to show that a given field is closed under finite unions, it's enough to show that it's closed under a union of 2 sets. a set A and a set B in F, if you take the union and that's in F, then, if they were generic sets, then you have shown that it's closed under finite unions. Because if you take three sets, maybe A, B, and C, and you want to take the union of all three, if it's closed under unions of two things, then you can union two things together, and that's still an F. And now you're left with two things. And so you can just talk about two things, and you can get to a union of n things by taking two at a time. So a field is a collection of subsets of omega that has three properties. It contains omega, it's closed under complements, and it's closed under finite unions. There are equivalent ways to define a field or algebra. Number one is that we can replace I of the definition with it contains the empty set rather than saying it contains omega. And this is because it's closed under complements. Because a field is closed under complements, if we exchange part I of this definition with that it contains the empty set, the complement of the empty set with respect to omega is omega. So we get the omega back and vice versa. So it's equivalent to have the sigma field containing an empty set or containing omega as property number one. Another thing we can change is property 3 of this definition. We had that it has to be closed under finite unions, and we can instead say it needs to be closed under finite intersections. The reason we can do this is due to De Morgan's laws. So imagine taking a set A and B out of F, and if it's closed under unions, we know that A union B is an F, but we want to show that A intersect B is an F. And if you intersect A and B and take the complement of that, that is equivalent to the union of the complements. So we took an A and a B in F. Because F is a field, A complement and B complement are in F. Because F is a field, the union of these two sets is in F, but this is all equivalent to the intersection. So it's closed under intersections. We get that by saying finite intersections. We get that by saying it's closed under finite unions. And we can get finite unions from saying it's closed under finite intersections. So we could replace part 3 of this definition with intersections as opposed to unions. If we replace 3, and now I'm actually not doing something equivalent, but defining something new. So I have a collection of subsets of omega that contains omega and is closed under complements. If we replace 3, which said closed under finite unions, with closed under countable unions, so possibly infinite, and a finite union is a countable union, then it goes from being called a field or algebra to being called a sigma field or sigma algebra. And you'll see this a lot in this course. We'll define something in terms of some finite action, and then we will kind of elevate it and say, we need this action to hold for a countable number of things, not necessarily finite, and suddenly we'll put a sigma in front of whatever we're talking about. So to go from a field to a sigma field, you need to exchange closed under finite unions with closed under countable unions. Let's look at some examples. Let's let omega be a non-empty set. One collection of subsets of omega that's really easy to deal with is omega and the empty set. And these together form a sigma field because number one, it contains omega. Number two, it's closed under complements. The complement of omega is the empty set, and the complement of the empty set in omega is omega. It's closed under any unions you want to take in here, even if you want to take several copies of the empty set in omega. If you have all empty sets, the union is going to be empty, but if you have at least one omega, the union is going to be omega. So this is closed under any countable union you want to form, and therefore it is a sigma field. And this is known as the trivial sigma field. A second example we've already talked about, and that is the power set of omega. So you have a set omega, and if you take any subset of omega, like the complement is necessarily another subset of omega. So everything is kind of already in there by definition if you take all possible subsets of omega. The third thing I want to talk about is going to be quite important for us in this course. I'm going to take any subset A of omega, and I'm going to form a collection of sets, F. I'm going to include A and A complement. and the empty set and omega. And that's enough to define a small sigma field because it contains omega. It's closed under complements. Take any one of these four sets, its complement is in here, and it's closed under any countable union of sets in here. This is known as the sigma field generated by A. And again, this is going to be a kind of important sigma field for us throughout this course. So if something is closed under countable unions, that could be countably infinite, but it could also be finite. So anything that is a sigma field is automatically a field, but not the other way around. Let's look at an example of something that is a field and not a sigma field. Let's let the space omega be just the real number line. And I'm going to let F be a collection of sets. I'm going to define it this way. I'm going to include the empty set and all finite disjoint unions of intervals of either this form, so open A to closed B, or this form, open A to infinity. And A needs to be less than B, and A could potentially be negative infinity. So for example, we know the interval minus infinity to infinity, the whole real line is in this collection of sets. So it already passes I for definition of a field. It is closed under complements. For one example, one particular set that's in this field, or so-called field, is the interval open A to closed B. And if you take the complement, that gives you a union of two intervals like this. And these are both in the definition of our sigma field. So it is still in the sigma field. Now, I'm not finished with showing property 2 because there's many other kinds of sets in there. Let's look at one more. Actually, let's look at all of them. So take any set A in F. It has to be either like this, so a finite union of half open, half closed sets, or like this, so any set of the form like A to infinity, both open, is in this set. Or in the third case, we can have something that looks like both of these union together. So we're trying to show that for one of these sets, the complement is also in F. So these are what are in the set by definition. And we want to show that the complement of all of these is still in the set, the collection of sets, the thing that I'm calling a field. So let's look at number 1, like a finite union of these disjoint intervals that are half open and half closed. The complement of this is this. So we have this part from minus infinity up to A1 closed, and this part open B1 to closed A2, etc. And this is a finite union of half open, half closed sets, which by definition is included in F. So if we take a set of this form in F, its complement is also of this form. Well, not exactly. We have a negative infinity, but yeah, the AI was allowed to be negative infinity. And that is also in F. So it appears that F is being closed under complements, but I do have the other cases to consider, and I'm gonna leave that to you. The third property is that it needs to be closed under finite unions. And I did talk about how it's sufficient to show that it's closed under a union of just 2 sets if they were really generic. But we have maybe different kinds of sets we have to consider. So let's look at a set that looks like this. It's going to be a union of n half open, half closed sets, and the interval open a n plus 1 to infinity, and also a half open, half closed interval a to b, which is maybe right in here. The union in this picture is everything between here and here, unioned with everything between here and here, unioned with everything up here. And this is one of the sets that we define to be an F. So closed under finite unions, I don't know that yet, but Here's an example of one complicated set in F. And we have shown that the union of these, that set with another set is still in F. So this doesn't completely, satisfy the definition yet of a field. There's more to be shown, but yeah, that's an exercise for another time. Now, this is a field. That's what we just sort of showed or claimed. And this was supposed to be an example of something that's not a sigma field. And that means that if that means we can find a countable collection of sets in F whose union is no longer in F. So I'm going to take a collection A1, A2, A3 defined like this: open from 0 to 1 minus 1 over n and closed on that side. If you union these together, then you have 0 to 0, and then you have 0 to 1/2, and then you have 0 to 2/3, and you keep stretching that interval and you're unioning them. And each interval is contained in the next. So you're just getting the last one, like the limit in this union. And you're never quite going to reach 1. The union, the infinite union here, consists of, it's an open interval from 0 to 1. And that was not one of the sets in our definition of F. So F is not a sigma field. What if we threw that set in? What if we define F as we defined it, and then we found like things that violate, being a field or sigma field? So we created new sets that are supposed to be in there but aren't, and then we throw them back in. We could sort of be building up a field or a sigma field. And in the next video, we're going to talk about a very special sigma field that is generated by a very special collection of sets known as Borel sets. I'll see you in the next one.